That's nice. Okay, so I would like to thank organizers for opportunity to present our recent results. So I will talk today about materials. So my topic is Chalcogenide colloidal quantum dots of lithium mercury for near and mid IR applications. So first of all, I want to give just a brief introduction what is colloidal quantum dots, in case that someone do not know. Colloidal quantum dots is semiconductor nanocrystals having optical electrical properties that change with the size of particles due to the quantum confinement effect. They sometimes referred as artificial atoms. What does it mean? So here to the left you see absorption and emission spectra of most popular quantum dots, actually cadmium selenide, and change in size from 3 nanometer to 5.5 nanometers. We can change absorption and emission spectra from blue to the red. Of course, optical properties depends both on material and size of nanocrystals, and depends on material. What you can see here in the right corner, you can have colloidal quantum dots for UV, for visible range, and for a near IR or mid IR applications. Of course, applications depends on properties mostly. At the moment, I suppose the most popular quantum dots are cadmium sulfide quantum dots, to selenide, of course. And because of its properties, it can be used for solar cells, it can be used for television, but if you see here at the left, with Chalcogenide quantum dots, you can reach also near IR and even far IR for something like mercury Telluride that is semi-metal and has zero gap, and so quite nice large exciton Bohr radius of about 40 nanometers. And near IR applications are useful for bioimaging, are useful for night vision, detection of some gases, and so on. So today I will present two topics that we finished recently. First topic is control agent of lead sulfide quantum dots. It was actually more serendipity. We started with development of new synthetic methods for lead sulfide quantum dots just by mixing sulfur in allylamine and lead oxide dissolved in oleic acid to prepare quantum dots. It works well. You can see kinetics of quantum dots growth. You can see temperature dependence and spectral development for different synthetic procedure. But suddenly we got that our samples sometimes very different, and this different comes mostly from the time from the synthesis to the workup. So we analyze situation very carefully and ended with screening for initiator of this change and who is responsible for blue shift that comes from time. As you can see on this picture, so starting material was at 1.8 microns, and if we add allylamine, nothing happened. acid some shift, both of them strong shift. It was also theory, and it's mentioned in the literature, that oxygen could be responsible for it as well, but it seems that it's not in this case, because both of adding some oxygen scavengers and degazing doesn't change the situation at all. So we found the initiator for this change, and then we decide to analyze the situation more carefully and to see what is it, this mixture of allylamine and allylic acid. Is it just mixture of two surfactants or just new compound? And this IR spectra shows us clearly that allylamine and allylic acid form new compound, allyl ammonium allyate, that is responsible for such changes. So then we try to analyze how it proceeds and how it can be used. So here you can see spectra of starting material and what you will find after 72 hours of storage. And to the left, development of maximum of first absorbance peak. And of course, question always important for colloidal quantum dots: how good is size distribution? Is it remains the same during the aging, or did it change? Crystals remain in the same morphology, or we got something new? So what you can see from those two TEM images, so they remain spherical, and it looks like entire size distribution just shifted to smaller size, from 8.5 nanometers to about 5 nanometers. So finally came the question, how better to use it, and what is advantage of our procedure. Actually, this procedure is very interesting opportunity to prepare a lot of different smaller size quantum dots just from one bigger quantum dots batch of lead sulfide, because normally to prepare lead sulfide quantum dots you need Schlenk technique, you need dry solvents, argon line, and so on. Here you can just take bigger quantum dots, you add a little bit of our magic mixture of allylic acid and allylamine, and after some time, depends on amount of mixture that was taken and time, you can get smaller quantum dots of any size. So next part of story is about tellurium, just as small intermediate. Tellurium is such nice metal that its names come from a Roman goddess of Earth. And tellurium nanocrystals are important nanocrystals because they're also mimics of a very popular material in IR detection, namely cadmium mercury telluride. And when you look in the telluride chemistry, you will find frequently such chemical equation that has actually no any reasons to draw except of analogy. And this reagent is used to make lead telluride, cadmium telluride, mercury telluride. But problem that tellurium is not metal. It's not like oxygen. It's not like sulfur. It's not like selenium. It's just different. And as we found, this picture is just wrong. what is published in all those estimated journals. So when we first try to prepare Tellurium nanocrystals and just decide to analyze a little bit all our precursors just to improve the entire procedures, we came to very strange NMR spectra. Because normally, when you dissolve in tellurium and triacylphosphine, you have 1 mole of tellurium, 2 mole of triacylphosphine, you would expect 2 signals in phosphorus spectra and doublet in tellurium. What you got? You got 1 singlet in phosphorus, 1 singlet in tellurium. So quite unusual. So that means that we have some kind of exchange process that is very fast on NMR scale. We try to analyze this situation. We try to slow down those exchange processes by lowering the temperature, by measuring NMR. It helped a little bit, but we got no splitting into signals. How we can see free Telluride? We can see free Telluride only when we just completely oxidized out all free phosphine. That is only the way. So from those observations, it's possible to suggest 2 pathways that explain all previous NMR spectra. Dissociative pathway, when tellurium comes to phosphorus and back and so on. Or associative pathway, where we have some kind of dance with changing pairs, and tellurium comes from one phosphine to another and then back and so on. Unfortunately, NMR itself cannot say which way is preferable. Therefore, we also did some DFT investigation, and DFT said as following. If we compare monomeric and dimeric structures with different chalcogenides, everything pretty similar up to selenium. So dimers like this one to the left are not favorable. But if you come to tellurium, it forms quite stable compound, at least stable enough to be intermediate. And this intermediate seems to be dominating species in our solution of tellurium. So knowledge is power. We just applied our solution for synthesis of mercury Telluride quantum dots for mid-IR application. Here you can see TEM image, and you can see absorption spectra. So they're about 3 microns, and we're able to tune the properties. So finally, what I presented here. So we developed new control agent methodology for the synthesis of lead sulfide quantum dots. It's very useful. You can make your own lead sulfide quantum dots by a very simple procedure. Also, we studied tellurium precursor in TOP with NMR, with quantum chemical calculation, and found new species. And having such knowledge, we were able to improve synthesis of mercury Telluride quantum dots. So finally, I want to thank my collaborators, and I want to thank my small team. And so here to the end you can see so how difficult is life and research in Russia in the cold winter, and my institute. So I want to thank you for your kind attention.
Okay, thank you for your presentation. Maybe there are some questions to Ivan Shuklov. Do anybody have some questions? Please raise your hands. Or
I can Igor, can I say a few words?
Yes, please.
I can just add something to last presentation of Ivan Shuklov. The application of newly developed quantum dots are various, and he did not told that now we actively collaborate in the field of applications of those quantum dots from the point of view of nonlinear optical properties. Now we analyze it with him nonlinear low-order nonlinear optical properties, and hopefully we will do the same with high-order nonlinear optical properties. We actively collaborate, and I hope that being in Riga, I will collaborate with Moscow Institute of Physics and Techniques more closely. Thank you.
I am waiting for new next Photonika conference in Riga, and we can present our results.